in general, those dynamics. Part 2, I'll definitely focus on climate change, the climate history that we understand here on Earth, and then the recent last 100 years when we've had good data to actually measure how the climate is changing. And then part 3 is climate communication. One of the big struggles about climate change is how to communicate climate change to the public, to help people understand and just understand and communicate to them that this isn't really a political issue. This is a scientific issue, something that's happening. And, this basically just talks about ways that we can talk to other people about climate change, hopefully without getting political about it, sticking more to the scientific realm. So atmospheric basics. First off here, I'll talk about the Earth and its spheres. The Earth's spheres is basically, we break them down into 4. The geosphere, that's basically, everything that's on the Earth's surface. The atmosphere, which is of course what we'll be focusing on. The hydrosphere, that's going to be everything that happens in all the lakes and the oceans on the planet here. And then the biosphere, that's everything that's living on the planet. And these all have impacts on the Earth and its climate. For the hydrosphere, of course, as most of you know, almost most of the Earth's surface is made up of oceans. That covers 71% of the Earth's surface. Of the available water that we have here on Earth, oceans account for 97.2% of the water on Earth, and all of that water is not drinkable. So the thing that's not necessarily in great supply is fresh water. And fresh water, a lot of it is stored in glaciers. A lot of it is stored in groundwater. And you see that a very tiny percentage is actually stored in lakes, rivers, atmosphere, so on and so forth. So just a tiny sliver of the available clean drinkable water is what basically supports our life here on Earth, what we all drink. The geosphere, again, consists of the solid Earth. It extends from the surface to the center, which is approximately 6,500 kilometers deep. The atmosphere is much, much less thick than the Earth itself. And we know way more about the atmosphere than we do what's happening inside the Earth. The deepest we've ever been able to drill into the Earth, I think, is really a puny 12 miles. We've never been able to take direct measurements of what's happening inside the Earth. We have a pretty good idea, or at least good theories about what's happening, but we know much more about what's happening on the surface of the Earth than we do what's happening on the inside. So, of course, the atmosphere is that very thin layer of air that's surrounding the geosphere. Our atmosphere, 99% of the atmosphere is within 30 kilometers of the Earth's surface. So we're talking less than 0.5% of the thickness, or the radius of the Earth itself. All weather occurs in the atmosphere, of course, and that's going to be in the troposphere. And this gives you an idea of the Earth's atmosphere, the entire atmosphere. What you see there in orange, very close to the Earth's surface, that's basically what we consider the livable part of the atmosphere. So this little area right here, this is where we all live and breathe and prosper. This is what supports life on Earth. Everything above that is technically the atmosphere of the Earth, but there's not much there that would support life. There is stuff there that protects us, just not stuff that we can breathe and live in. The importance of the atmosphere, it does moderate temperatures on this planet. If we didn't have an atmosphere, based on our distance from the sun, our global average temperature would be about 0 degrees Fahrenheit, with huge temperature swings, pretty similar to the moon's climate. So, without an atmosphere, outside of not being able to breathe, everything would be well below freezing. So we wouldn't have liquid water on the planet. With the atmosphere, our global temperature is on average 60 degrees Fahrenheit, and we don't have major temperature swings. Most of our temperature swings on any given day between daytime and nighttime are within the 20 to 30 degree Fahrenheit range. Point 2 is that the atmosphere offers us protection from solar radiation. basically shields us against harmful UV radiation. That's largely what the ozone layer does, is it wipes out a lot of that shortwave radiation that could give us cancer. If we think about the importance of the atmosphere, considering survival time, what we as humans can survive without, without food, we could survive a few weeks, technically. Might not be a pleasant few weeks, but we could still survive. Without water, we can only survive a couple, maybe a few days. Without air, we can only survive a minute or two. So again, the importance of the atmosphere, what we're all breathing, it's very important to maintain the chemical balance of what we have in the atmosphere if we want to be able to, live and breathe like we are now. Of course, the Earth's biosphere, everything that I've talked about, the geosphere, the atmosphere, the hydrosphere, all of that impacts life on Earth. Anything from the ocean floor, boiling hot springs, air currents in the lower atmosphere, life is everywhere on this planet. And so anything that happens in the atmosphere affects all the spheres of our planet. And again, all of these spheres, they interact and have a significant impact on our weather. One of the biggest things we look at, one of the big drivers of what we call weather is, of course, water vapor in the atmosphere. And we can see this in what we call the water cycle. So as far as we know, all the water that's been on Earth has always been on Earth, and it's just recycled over and over and over again. So the same water you're drinking today is the same water dinosaurs drank millions and millions of years ago. So water just keeps getting recycled through the Earth. Basically we get clouds from evaporation from oceans, any freshwater surfaces, also from vegetation. It breathes water vapor into the air. You'll notice occasionally here in Arkansas, we get hot and humid. Part of that is because of the lush vegetation that we have across the state. Also because of the proximity of the Gulf of Mexico that brings quite a bit of moisture up north here over the state. Once we get clouds, eventually those clouds grow deep enough. They develop enough water droplets that results in rain, and that puts the water that was evaporated into the atmosphere back onto the ground, into the groundwater, and then back into the oceans and freshwater surfaces. And this cycle just keeps moving over and over again. No matter what we do to it, eventually things, water turns, no matter how we use it, the water goes back into where it began, back into the fresh or ocean water, origins. This is a view from the International Space Station, sort of gives you a nice perspective on how fragile our atmosphere is. You can see the Earth, you can see the hydrosphere, the geosphere, very, very large in comparison to the atmosphere. So the atmosphere is just this thin little blue line on top of our planet that protects and supports all of the life that we have. Here's basically a vertical view of what's in that thin little blue layer. Where most of us live here is within the planetary boundary layer, so the lowest kilometer of from the Earth's surface. This is where most of us stay, live, and breathe almost all of our lives. That's basically where we feel the direct impacts of weather, where it's raining on us, snowing. We get thunderstorms, things like that. Most commercial aircraft fly at the very top of the livable atmosphere in what we call the tropopause. So where most of us live is in the lowest 10 kilometers. This is what supports life on the planet. Commercial aircraft fly right at the top of that. Humans can technically survive, but it gets tough. We've had humans survive the climb to Mount Everest, which is about the same height as commercial aircraft, but getting up there is very difficult, and many people have died making that trek up into Mount Everest. Once we get above the tropopause, we get into the stratosphere, and the chemical composition of the atmosphere changes dramatically, and that is not survivable. There's not enough oxygen there to support life. Of course, there is a form of oxygen, it's ozone, but ozone is not something that we can breathe. It's a different chemical form of oxygen, and so it's 3 molecules of oxygen instead of 2 combined with one another. Makes a big difference. When we launch weather balloons, they make it up into the stratosphere before they pop, and that's where you're getting some really, really low air pressure. There's not much air above a weather balloon here, so we're getting up to most of the Earth's atmosphere is from the top of a weather balloon down to the surface. Most of our satellites still technically exist where we can measure molecules of air or molecules of atmosphere from the Earth. Most spacecraft will exist in between the thermosphere and the exosphere. Once you get beyond 1,000 kilometers, that's technically what we would consider outer space. Outside of any impact or any detectable signs of atmosphere, associated with the Earth. So again, the troposphere is where we all live and breathe. In general, the temperature decreases with height in the troposphere, with a general decrease in height of about 6.5 degrees Celsius per kilometer. That's why your mountains typically have snow caps on them, because it's very cold as you get higher up in the atmosphere. The tropopause marks the top of the livable atmosphere, the troposphere, and also generally marks the lowest temperature. Once you get into the stratosphere, the temperature actually increases with height. So we actually get warmer as we get into the stratosphere. Of course, the density of the air is not very great. Again, it's not livable. So the fact that the temperature increases doesn't mean you would feel warm necessarily. There's hardly any air pressure there. But the main reason why the temperature increases within the stratosphere is because the ozone layer is absorbing high energy radiation. And so that high energy radiation gets absorbed and refracted or re-radiated back out into space from the ozone layer. And that protects us from a lot of the harmful parts of the sun's radiation. The sun primarily radiates in the visible spectrum, which is, again, why that's how life on Earth has sort of evolved to take advantage of that, is because that's the peak radiation point of the sun. But the things that are harmful, the gamma rays, X-rays, things like that, the sun also radiates those things, just in a lesser quantity. However, all of that would be very harmful to us if it wasn't for the ozone layer. So the ozone layer filters out those X-rays and gamma rays that would destroy cellular life on Earth if it were able to make it to the ground. Once we get into the mesosphere and the thermosphere, these are basically parts where you would basically consider it space. You wouldn't technically be in the part of the atmosphere where you could live or breathe or actually see the air. Like the sun wouldn't be refracted, so it wouldn't be blue anymore. It would almost look clear, or again, like you were in space. Some of the things that happen here is we have the ionosphere up at this level, and this is ham radio operators can take advantage of the ionosphere to bounce radio waves off of to reach far distances. So you can bounce radio waves from the ground off the ionosphere back to other parts of the Earth to reach countries on the other side of the world that you normally wouldn't be able to reach. Again, technically, space begins in what we call the thermosphere. And even our International Space Station, it exists in technically a part of the atmosphere, although it's, again, the atmosphere has such low density, you wouldn't be able to see anything. The highest part of the atmosphere we can actually see is the Aurora Borealis. That's at about 100 kilometers up. This is, again, where the sun's radiation interacts with our ionosphere, and we can see some of those magnetic waves be energized in what we call the Aurora Borealis, and this occurs most frequently at the very high and low altitudes of the Earth. When we see meteors, it's actually lower into the Earth. Meteors don't start to break up and create streaks until they hit a little bit higher air density. And so they start to break up below the thermosphere, below the Aurora Borealis in the mesosphere. Most of them don't make it into the stratosphere. If they do make it into the troposphere, they're encountering an incredible amount of air or wind resistance, and that's what causes them to flash very bright and start to burn up. Most of them don't reach the ground because of just the high density of air molecules once you get closer to the Earth's surface. So again, this is the vertical temperature profile of all of the layers of the atmosphere. The troposphere is where, again, all life on Earth pretty much exists, and the temperature in general decreases with height. And then the ozone layer occurs within the middle of the stratosphere, where that temperature starts to increase with height. And again, most meteors start to disintegrate in the mesosphere, which is right above the ozone layer. Pressure changes. So air pressure is one of the things that we measure as meteorologists. And air pressure is basically just the weight of air on top of your head at any point in Earth. So if you're at or near sea level, it makes sense that you've got the whole atmosphere of the Earth pressing down on your head. And again, we were born, we developed, we evolved on this planet with all this air on top of our head. So we are very well accustomed to that weight of air on us. So we don't even feel it. It doesn't affect us at all. We feel like we can move pretty freely without feeling the air on top of us. However, if you went up to Mount Everest, you would notice that all of a sudden you don't have as much. It's not so easy to live and breathe, and things start to happen to you. If you've ever been on an airplane, they pressurize airplanes to about 850 millibars, and even though airplanes are flying up there near the top of Mount Everest, your ears pop, even with just the loss of 150 millibars of air pressure. If they let the air pressure drop to the actual pressure that airplanes were flying at, most people would pass out due to the rapid loss in air pressure, just because our bodies are not used to having air pressure decrease that quickly. So again, most of us live down here near sea level or a few thousand feet above that. And so we generally have anywhere from 1,000 to 850 millibars of air pressure on top of us anywhere we travel on the planet. The composition of the atmosphere, most of our atmosphere is nitrogen. Then, of course, about 20.1% of it is oxygen. That's the part that we need to live and breathe. Nitrogen is very important for especially vegetation on Earth. But in general, the nitrogen is inert. When we breathe it in, it doesn't do anything in our bodies. The oxygen, of course, is very important. Carbon dioxide is right now at 412 parts per million. That's only 0.04% of the atmosphere. But as we'll talk about, that number keeps increasing steadily here and plays a very important role on how warm we're getting on the planet. The other major component of the atmosphere is argon. Again, that's inert, so it doesn't really do much to us, doesn't change much in percentage. And then otherwise, we have other inert elements like neon and helium, but we also have methane, which is another thing that's going to, even though it's in a very small quantity, 1.5 parts per million, it plays a role. It's a greenhouse gas. It's something that will cause the temperature on the surface of the Earth to increase. If we compare the Earth's atmospheric or chemical composition with other nearby planets, we can see that Venus that's basically an example of runaway greenhouse effect. When carbon dioxide makes up 96% of the atmosphere, I want to say the Russians maybe have gotten a couple of probes down to Venus's surface. They've only lasted maybe 10 minutes before they were destroyed. We know that the surface of Venus is somewhere around 700 degrees Fahrenheit because those probes were able to survive down to the surface. But the carbon dioxide has trapped so much heat on the surface of Venus that no life as we understand it can exist. It's too hot. Of course, water can't exist in any form really with temperatures that high. It technically could exist as a vapor, I guess, but there's not much of it on Venus. Most of the atmosphere is carbon dioxide. A small percentage is nitrogen. Then there's just a trace amount of oxygen that we've been able to detect in the atmosphere. Now, Venus has a very thick atmosphere. Mars has almost no atmosphere anymore, but the atmosphere that is there is 95% carbon dioxide. The reason why Mars isn't super hot is just because it's so far away from the sun. We do have probes and robots on Mars that easily survive, but where the air pressure on Earth is something like 1,000 millibars, the air pressure on Mars, the entire depth of the atmosphere, is only about 8 millibars. So there's just not much atmosphere there. So even though the atmosphere is primarily composed of carbon dioxide, there's not enough of it there to create a runaway greenhouse effect like we have on Venus. There is some nitrogen on Mars, even a little bit of oxygen, but methane on both planets is 0. And as we understand, methane is produced by living organisms. So no atmospheric signs of life on Venus or Mars. And of course, we have probes on Mars looking for any signs of ancient life. Did something change on Mars? Did something happen where it used to support life, but it no longer does? The variable components of our atmosphere, of course, are a water vapor. That can change anywhere from 0 to 4% by volume, depending on where you are on the planet, how close ocean or water sources are, and how often you're getting clouds and precipitation. Aerosols, they're very small, solid and liquid particles. Basically, anything that can float up into the atmosphere is considered an aerosol. Some of these can absorb radiation. So volcanic ash is an example of an aerosol, and that generally would block radiation from reaching the surface. So that could cause things to cool. But things like dust, soot, and sea salts, some of those are important because they basically serve as tiny surfaces for water to collect on, and it plays a large role in creating, allowing water to get heavy enough to fall as rain on the planet. If we didn't have some of these aerosols, we wouldn't get as much precipitation as we do, especially away from the tropical areas. And of course, ozone is variable as well. Of course, it's in the stratosphere, but we heard a lot of talks about holes in the ozone layer and things like that. Luckily, where we've had holes in the ozone layer, they've been over parts of the Earth where there's not much life, largely over Antarctica and maybe parts of the North Pole at times. We have not had any significant holes in the ozone layer so far over parts of the Earth where we have a lot of people living. Carbon dioxide, even though it makes up only 0.04% of the atmosphere, it does absorb quite a bit of thermal energy as the sun's energy hits the Earth's surface. The Earth's surface heats up and then re-radiates that energy back up into the air as thermal energy or infrared energy. And carbon dioxide is an excellent absorber of that type of energy. So carbon dioxide in the atmosphere absorbs thermal energy and then re-radiates that back down to the ground. So because the more carbon dioxide we have in the atmosphere, the more thermal energy we're having re-radiated back to the ground from the air. So it's basically a feedback cycle that can keep the Earth warmer than it normally would be. The reason why carbon dioxide is rising in such rapid levels here is that we're producing more carbon dioxide right now than the Earth's natural carbon cycle can consume. And we'll talk about this a little bit in the second part, but there was a period on Earth where we had even more carbon dioxide than we have now, but the Earth was in a very different state at that time. Basically, here's the general carbon cycle. Some of the carbon cycle is pretty natural. for instance, life on Earth breathes like humans. We breathe out carbon dioxide. Our body uses oxygen. We breathe out carbon dioxide. So that's one source of carbon dioxide, not a major one, but it is a source. Photosynthesis and respiration of marine organisms is a source and sink of carbon dioxide. Volcanic activity, weathering of carbonate type rocks, and of course natural wildfires are big sources of carbon dioxide. But one of the big ones right now that the Earth is not able to keep up with in its natural carbon cycle is the burning of fossil fuels. So if it wasn't for the burning of fossil fuels, the Earth is pretty much ready to take care of itself in terms of the amount of carbon dioxide in the atmosphere. The Earth, again, the life on this planet has sort of equalized and adapted to being able to process and use carbon dioxide to keep the balance in place. So the Earth wildfires are a natural thing. So the Earth is used to wildfires and can process that carbon dioxide that's released from those. And volcanoes are a normal thing on Earth. So it can handle volcanic eruptions. But burning of fossil fuels, since it's so consistent and it's not natural, that's where the Earth is having trouble keeping up. The Earth and the life on Earth can't evolve quick enough to keep up with the amount of carbon dioxide we're releasing into the atmosphere. Again, the greenhouse gases, the things that we're worried about that are going to warm up the atmosphere on a pretty consistent basis. Carbon dioxide is the most prevalent, currently at 412 parts per million. However, methane and nitrous oxide are significantly more potent greenhouse gases, but they are in much lower concentration than carbon dioxide. Of course, methane is produced by living organisms, so we do have a consistent source of methane, and it can be produced by some industrial methods, but mainly carbon dioxide is the most common thing of just simple burning of fossilized fuels from millions of years ago is what we're burning into the atmosphere. So carbon dioxide, even though it's not necessarily the most efficient greenhouse gas, it is considered the most dangerous because there's more of it and it's growing more rapidly than the other more efficient greenhouse gases. Here's basically the current projections on how our carbon dioxide levels are going to change over the Earth over the next 100 years or so. Basically, if we don't do anything, if we just continue business as usual, you can see that the projection by the year 2100 is that we have 910 parts per million of carbon dioxide in the atmosphere. So a little more than double of what we have right now. That would, as far as our models tell us, that would increase the global average temperature by 8.1 degrees Fahrenheit, that's pretty bad. I'm not certain that ice caps can exist on the planet if it's that warm. It's not that the Earth isn't livable. It's not going to kill all life on Earth, but it is sort of like our current pandemic is forcing a new normal upon us. Life would be dramatically affected by a big increase in sea levels and global temperature, where we'd all have to live as a society in a new normal in a very much warmer Earth. There are things that we can do, of course, to limit carbon dioxide emissions, but it relies on us in the United States, a major carbon dioxide producer, to either find new sources of energy or to limit, change some of our behaviors like driving everywhere, flying everywhere, or at least change how our cars are using energy to electric or something that's not producing, not burning fossil fuels. Again, a lot of this is easier said than done. It's hard to just switch out all the millions of cars we have in this country to something else, but it also relies on other industrial countries to do the same. So China, Europe, they'd all have to be on board to make a major impact here. It is possible that if we switched the whole Earth to clean energy sources very quickly, we could actually lower the amount of carbon dioxide in the atmosphere, but that's probably pretty unlikely. The INDC strict, basically, if all countries adhered to limiting the amount of carbon dioxide output and to implementing as many clean energy sources as possible, that would tend to sort of flatten the curve, as we've heard here from the pandemic, where we'd still have carbon dioxide increases, but in 100 years, that would only result in a temperature increase of about 1.5 degrees Celsius to 1.8 degrees Celsius, which is something we could probably deal with. It wouldn't result in as huge of a sea level rises as business as usual would. Of course, the greenhouse effect, we all know how a greenhouse works. The glass basically allows the visible energy into the greenhouse, but then as that visible light energy is transferred into heat energy, into infrared energy, glass is insulated from infrared energy. So as the ground or the plants release infrared energy, it basically is absorbed by the glass and re-radiated back into the greenhouse. So that's what keeps a greenhouse warm. And that's basically what carbon dioxide does in the atmosphere, is it absorbs infrared radiation and re-radiates that back down to the ground. And this is, I don't know if you'll be able to see this, but this is just a short video showing you what we're doing to create increase the greenhouse effect across this planet. If this video doesn't work, maybe I just will skip future ones, but we'll see what this does here.
Dennis, is it supposed to have sound?
Yes. Is that not playing for you?
It's not.
Oh, okay. Well, okay. I'll just skip this then. We've talked about most of it anyways. Okay, so skipping that, we'll just talk about the briefly here about the difference between meteorology, weather, and climate. Meteorology, in a general sense, is any study of the atmosphere. So that could be weather or climate. At the National Weather Service, we, as the name implies, we study weather. So basically, we're worried about the state of the atmosphere right now at any given time or place, and then what's going to happen over the next 7 days. Climate, on the other hand, deals more with average weather. It's not very concerned with what's happening over the course of a number of days. It's worried about what's going to happen over the course of a number of years, or hundreds of years, or even thousands of years. The climate, we can get a generalized weather variation for a given place for some of the known climate forcers, like the El Nino Southern Oscillation can have a big impact on some of the average weather we experience here across the United States. But climate data cannot predict weather. If you know the averages for a particular point on Earth, for instance, we know the temperatures over Antarctica are going to, on average, be much colder than the temperatures in Peru, right? So we can understand some of those things, but in general, climate cannot predict day-to-day weather. It doesn't have any predictive, anything that's going to tell us the high today is going to be 72 degrees. That, climate can't do that. It can give you longer-term trend forecasts, like how the average temperature across the whole Earth might change over a period of time. When we're looking at weather, we're tracking things like temperature, humidity, where it's raining, snowing, things like that. And we can have some pretty big temperature and precipitation swings within the course of a week. So big temperature changes and weather changes occur along fronts, warm fronts, cold fronts, where we have significant precipitation that allows cold air to move long distances, like out of Canada into the central United States is a very common one. But again, this is not really forced by climate. This is more of a short-term changes in the atmosphere that we call weather. Some of the examples here of weather versus climate, thunderstorms, snowstorms, flooding, hurricanes, fronts. These are all examples of weather, things that climate can't predict and can't readily explain. Now, things like heat waves, that kind of gets bridged in between weather and climate. Long-term heat waves may be able to be explained by climate, but those short-term heat waves are more on the weather spectrum. When we do look at climate, we're looking at more long-term effects of things. For instance, the El Nino Southern Oscillation, which is basically the temperature of the ocean water near the equator and the Pacific Ocean. That's how we measure the El Nino Southern Oscillation. That plays a large role in how air currents move over the northern hemisphere. And it has a direct impact, especially on large-scale weather patterns over the United States. Things like the Dust Bowl, that was a big climate forcer, so that occurred over a number of years. And it wasn't just climate that played a role in that, but a lot of anthropogenic forcing, like really terrible farming practices, removing trees, or not having windbreaks, extensive drought. All of these were positive feedback mechanisms that led to a worldwide disaster, depression, and shortage of food across the United States and other parts of the world. And then, when we're measuring the average temperature over the number of several years, like this map here on the bottom left, this is another measure of climate, how temperatures are changing over decades instead of over, a few days. And I don't know if there's any audio with this, but if not, I can at least talk over this one. So basically what this video is going to show you is the difference between climate and weather. So the path of the dog is more weather, how the dog's path changes quite a bit, with time, has big ups and downs. But you can see that the person walking the dog, that's more of an average. So the person walking the dog represents climate, whereas the dog itself, the path it takes, that's more of a measure of weather. So if you follow the path of the dog, if you follow that over short-term changes, it might look like the temperature is greatly decreasing or increasing with time. But if we follow just the path of the dog walker, that's basically climate. So on average, we can see that general trend is up, but then the dog's path was up and down and all over the place. So when we talk about climate, it's important not to look at short-term weather trends, but to follow those longer average trends. Now, some of the basic things to understand about climate and what drives long-term, basically the energy budget, long-term changes in the seasons on the Earth here, is understanding, what drives, our diurnal changes in temperature. So the Earth's two principal motions are, one of them is rotation. This is what gives us night and day. Of course, this is the Earth spinning on its axis, changing which part of the Earth is pointed towards the sun at any given time. This is, of course, what we experience as day and night. One full rotation of the Earth is what we refer to as a day. So that's 24 hours. That's one full rotation of the Earth. And then there's, instead of rotation, so the Earth is always rotating along its axis, but it's also revolving around the sun in an elliptical orbit. And every trip, every lap we make around the sun is what we call as humans 1 year. When the Earth is closest to the sun, perihelion, that occurs during our winter. So that's actually on January 3rd. And the aphelion is basically when the Earth is furthest away from the sun, and that's actually during our summer. And so one of the misconceptions is that during our summer, the Earth is closer to the sun, which is what makes the temperatures warmer. But that's not true. Actually, during the summer, we are the furthest away from the sun. The Earth is. So we're actually getting a little bit less solar energy than we do during the winter. I know it sounds weird, but I'll explain here. What drives the seasons is the tilt of the Earth. So basically, here's the Earth's orbit, and it changes over the period of a long period of time. It will change, on the order of hundreds of thousands to millions of years. And the Earth has had different orbits around the sun throughout time, from what we can tell through long-term climate records. But right now, I guess the shape of the Earth's orbit around the sun is more circular than oval. Although it is still technically an ellipse, it's more of a circle, closer to a circle than an ellipse than it has been in the past. The Earth's position in this orbit, again, it will change on a time scale from what we can tell about every 23,000 years, much longer than anything we'd experience in the average human life, of course. The tilt of the Earth's axis changes a little bit as well. Currently, it's at 23.5 degrees off of being straight up and down, or off nadir. But it's sort of like a spinning top that's slowing down. And so that axis might change a little bit, but again, nothing that's going to affect us during our lifetimes. The combination of the Earth's orbit changing and the tilt changing is something that's called the Milankovitch cycle. Haven't read that paper myself, but apparently that's the main researcher of that phenomenon. Again, that's something that's going to affect climate over the course of hundreds of thousands of years. Hopefully people will still be around, but again, we'll be more worried about what's going to happen in our lifetime and the lifetimes of our immediate descendants, our children, grandchildren, and great-grandchildren. Our current orbital cycle, again, is more circular than oval-shaped. Our summer solstice occurs in the northern hemisphere when we're the furthest away from the sun. And again, that misconception that our closeness to the Earth has anything to do with our temperatures, that's not really true. It's the tilt of the Earth when the northern hemisphere is facing the sun is what drives our seasons. And so here's an example of basically the sun angle compared to different times of the year. So during the summer solstice in the northern hemisphere, just looking at a latitude of about 40 degrees, which is a little bit further north than us. Basically, we see our longest day is in the middle of June. It's what we call the summer solstice, or late June, I should say, and that's when the sun angle at noon is at its greatest. So at 73.5 degrees from being straight overhead, that allows the sun's energy to reach the ground much more efficiently because it has less atmosphere to go through. If we look at the winter solstice, the sun's angle during noontime is at a much lower angle. It's only at 33.5 degrees. So the sun's energy has to travel through a lot more atmosphere before it reaches the Earth, resulting in cooler temperatures on average. So again, the gradual change in the length of days accounts for some of the differences of the seasons. The big role of that is the change in the angle of the sun. But the Earth heating up, it stores some of that heat, so that lags our peak heating season a little bit behind the solstices. So even though our the highest angle of the sun at noon over our latitude happens to be in late June, the fact that the Earth has stored so much heat energy that drags the season where we actually see our peak temperatures into July and August, and we don't really start to feel the effects of that lower sun angle until we get into September and October. Here's a basic illustration of why the Earth is why the northern hemisphere is warmer during what we call our summer months than the winter months. That sun angle changes the depth of the atmosphere that the sun's energy has to go through to reach the Earth's surface. During the summer, again, that path of the sun's energy through the atmosphere is significantly reduced compared to the winter, where the energy has to travel through a lot more atmosphere just due to the angle to reach the Earth's surface. So if we compare the two, the summer sun filtering of the atmosphere is significantly less than the winter sun filtering. So basically, the atmosphere absorbs and refracts more energy during the winter than it does during the summer. And so that allows the Earth during the summer in the northern hemisphere to absorb more energy and to heat up than it does during the winter, where more of that energy is absorbed and released back into space. And again, the Earth's orientation and tilt is constant. It's 23.5 degrees off being straight up and down. And so basically that constant tilt of the Earth as it revolves around the sun, that changes the exposure of which hemisphere is receiving the most sun energy at any time of the year. So during the winter solstice, that's when the northern hemisphere is tilted away from the center of the sun's radiation. And so again, the sun has to go through more atmosphere before it gets to us. We get less energy, and of course, that's why we end up being colder. Basically the center of the sun's energy will travel between 23.5 degrees north and 23.5 degrees south latitude, and we refer to that as those latitudes as the Tropic of Cancer and the Tropic of Capricorn. So during our summer months, the sun's direct energy is at the Tropic of Cancer, 23.5 degrees north latitude, and during the winter months, the center of the sun's energy is at the Tropic of Capricorn. The only time that changes the amount of daylight we have, and it changes the amount of sun's energy that reaches the Earth's surface. And at the equator, that's the only point on the Earth where the amount of daylight hours never changes. It's always 12 hours of daylight, 12 hours of nighttime. So that's why the equator is always very, very stable in terms of temperature. The sun's angle changes a little bit with respect to the equator, but in general, that consistency of daylight hours makes the temperatures in 0 degrees latitude makes it hardly ever change. So it's just almost constantly warm and humid at that latitude. Oops. What did I do here? Okay. We'll see if this works. I'm going to click on this, see if it will allow me to show this to you. Let's see. Can you see what just popped up, or are you still seeing the PowerPoint presentation?
Still seeing the PowerPoint.
Yeah.
Okay. 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 How about now? Did that show up?
Yeah, it changed.
Okay. So this is, let me click on the Earth here, and I'll speed it up. So this is basically at about 40 degrees north latitude. This is basically how the Earth, how the Earth in the northern hemisphere, how we experience seasons. So again, that constant tilt of the Earth never changes. You can see how as the Earth revolves around the sun, how different parts of the northern hemisphere are exposed to longer daylight hours and a shorter sun angle. And you can see how that's changing temperatures. That's the thermometer on the right-hand side here. During the summer, our average temperature is, warmer than mild. And then as we get into the winter, our average temperature is cooler than mild. Now, if you change latitude, as you go further north, during the winter, there's if you get above the Arctic Circle, there's no daylight at all. So it gets very cold. And then as you get into the summer, it's 24 hours of daylight. So your temperature is on average, much warmer. Now, if we look at a planet like Venus, to where it basically has no tilt at all, it's tilted at its inclination angle is 2 degrees, there's hardly ever any change in temperature. So if the Earth didn't have a tilt, basically we wouldn't have seasons. We would always be in a constant, spring or fall like temperature here. We would always be mild. And some of us might prefer that, right? We wouldn't have the super hot summers. We wouldn't have the super cold winters, but the weather would be kind of boring. We would almost always be the same. So that's Venus. There's precedent for that type of tilt, in our solar system. The other extreme would be Uranus, which is tilted completely on its side. So if the Earth was like that, the northern hemisphere during the summer would be would have 24 hours of daylight, would be extremely hot. And then during our winter, we would have 24 hours of nighttime. So we would be extremely cold. And so we would have massive temperature swings on Earth, where the northern hemisphere, almost all the water would freeze. And during the summer, almost all the water would exist as a water vapor. So that would probably make life a little bit difficult to exist on the planet. So on Earth, we do have our nice seasons here. Gives us a nice variety of weather, and also gives us a break from the heat and a reprieve from the cold, and hopefully gives everybody a little taste of what they like. If not, you can always move to the equator, right?
Right.
Okay, let me go back to the presentation here. So that's all I've got right now for atmospheric basics. If you guys have any questions, I'll be happy to talk to you about it. If not, go to the bathroom, grab a cup of coffee, some water, whatever you want to do.
You want to put any questions in the chat, please do, and then we'll handle them after the break. So just
Sounds
write
good.
your questions into the chat.
Okay. Take 10, y'all.
Anne, are you there?
Yes.
For some reason, I can't, this Jana Marie, I can't get my keyboard to work, but I wondered if this is going to be recorded.
It is recording right now, actually.
Awesome. Thank you so much.
Yeah.
Carbon dating, some of it is analyzing, layers, tectonics, lots of different sciences coming together. Have estimated the origin of the Earth or the beginning or the age of the Earth to be about 4.55 billion years old and counting. Our climate history, we have theories about what happened for the first 4 billion years, but we don't really know. A lot of that is based in theory. It may not be super relevant to what's happening today. Especially with some of the very catastrophic things that have happened or we think have happened to Earth in the first 4 billion years, including maybe mini planetary collision that may have resulted in the formation of the moon. I'm sure the climate wasn't all that hospitable during that time. But, I've heard things like snowball Earth occurred billions of years ago, things like that. So at least for life and fossils that we can measure on Earth, we have some climate record for about the last 500 million years or so, which is still good, but not perfect, I guess. A lot of the controls on the climate that we understand have involved tectonic activity, changes in orbital cycles, solar irradiance, basically changes in sun cycles, sunspots, and then, of course, changes in atmospheric composition. Timescales of climate change, again, that historical scale is more what we actually have data to back up, what we can take ice cores. We actually have direct weather observations. The deglacial millennial scale, that's coming out of the ice age, basically. The orbital scale, that's, we're getting further back into time. As we get further back into time, more, more guessing or more scientific guessing comes into that, more theory. And then the tectonic scale, again, we're talking much larger scales of time, actually changing the shape of the continents and things like that. Some of the things that we understand about the Earth's climate system are the forcing and response to how things are changing the Earth's climate. Some of the natural forcings, of course, plate tectonics, orbital cycles, solar radiation. We don't have any control over those things. That's just going to happen. And so those are all parts of the natural climate forcings. Some of the internal interactions, of course, is we have this atmosphere, vegetation, ocean, surface land use, and ice interchange. And some of the human-caused forcings, the anthropogenic forcings, are the changes in how we're using the land. So every time we lay down concrete, that changes how the Earth absorbs energy. Every time we burn fossil fuels, that changes the composition of the atmosphere on Earth. The ocean stores quite a bit of heat, so there's some carbon dioxide production there. Of course, there's lots of life, lots of plant life in the ocean as well. So that's a source of oxygen and carbon dioxide. We get weathering, again, CO2, sulfur dioxide production from volcanoes. We have underground volcanoes as well that produce carbon dioxide that eventually gets released into the air. And, the melting of sea ice also releases some carbon dioxide that's been stored in the ice as well. Responses and changes too. Of course, every time we change the climate, that's going to have an impact on the atmosphere, how much land or sea ice we have, the type of vegetation that can survive in any particular point on the Earth. It can basically change land surface, any of the spheres we talked about, the climate is going to impact. As we understand, sunspots and solar output changes, we've had some big changes throughout history. We have some sort of reliable record for the last 400 years or so. Sunspots are basically areas of intense magnetic activity, based on telescopes, Galileo type times and to modern times. We know that dark spots on the sun's surface, those sunspots do correlate to solar radiation. And we know that the sun's sunspot cycle is on about an 11-year cycle. Through the late 1600s into the early 1700s, we had, basically astronomers recorded very low sunspot activity, and increasing activity, could have helped explain some of the increased temperatures by anywhere from a few hundredths to a couple of tenths of a degree Celsius in the 20th century. The radiative forcing of changes in solar activity is on the order of, and again, we're measuring energy here. So the energy produced by the sun is measured in watts, sort of like we measure the energy from a light bulb, but it's in watts over an area. So every square meter of the Earth. So it's 5/100ths of a watt per meter squared. The radiative forcing from carbon dioxide alone, you can see, is hundreds of times more, hundreds of times more effect than some of the subtle changes that we see in solar activity. So while sunspots and solar activity can explain some aspects of warming in the 20th century, the increase in carbon dioxide is orders and orders of magnitude greater, has more forcing in the increase in temperature on the planet than changes in solar activity. So changes in solar activity are real, they just haven't changed the temperature by that much. And then the radiative forcing of all greenhouse gases, that includes some of the some of the other greenhouse gases we talked about, like methane, nitrous dioxide, that increases it even more to 2.65 watts per meter squared. So we can actually filter out the greenhouse gases and see that has a much larger role and can, determining what the Earth's climate is going to be like compared to changes in, at least subtle changes that we've measured in sunspot activity. So basically our carbon cycle, on Earth, of course, the vegetation and even in the oceans, the algae is going to convert carbon dioxide into oxygen. Of course, you have natural carbon emissions from any life on the planet is going to be converting oxygen into carbon dioxide. Any non-vegetative life anyways. You've got microbial respiration and decomposition that explains some carbon emission. Of course, you have human emissions of carbon, and one of the reasons why human emissions aren't being accounted for by the other life on the planet is that basically we've got all this fossilized carbon that's stored way beneath the Earth's surface. That's not a part of the normal climate cycle or the normal carbon cycle. I'm sorry. What we're doing is we're drilling deep into the Earth's surface and we're taking this fossilized carbon and we're transforming that carbon that's stored deep in the Earth's surface, protected from the carbon cycle, and we're releasing that into the atmosphere. So it's not like we're creating carbon dioxide from nothing. It's that the Earth's history, things that have died thousands and thousands of years ago, but have that carbon stored up under many layers of soil so that it's basically protected from the atmosphere, not interacting with the carbon cycle. We're now releasing that in mass quantities into the atmosphere so that the normal carbon cycle on the Earth, the ocean and the vegetation, conversion of carbon dioxide into oxygen, so on and so forth, cannot keep up with what we are digging into the Earth and releasing carbon dioxide into the atmosphere. So that's basically the problem, is all of this stuff that's stored deep in the Earth's surface, we're now releasing into the atmosphere as carbon dioxide. Whereas there's nothing replacing, of course, the fossil fuels in the Earth's surface. We're just changing that into carbon dioxide. Again, the carbon cycle, again, includes vegetation, natural wildfires, human emissions, and of course, gas exchanges from the ocean. The ocean stores a lot of carbon dioxide. Of course, it's also a great source of oxygen as well from the life that's in the ocean. The sensitivity of the global temperature to carbon dioxide, we know that at low carbon dioxide, we need some, basically. Carbon dioxide, the greenhouse effect is important because without the atmosphere, without any greenhouse effect, the Earth would be almost completely ice, which again might support life in the oceans, beneath the surface of the ice, but it isn't going to support much terrestrial life. So we need land, we need liquid water on the Earth's surface in order to support life. So we do need some carbon dioxide in the atmosphere. It's not like we want to scrub it all out. It's that, the balance of how much carbon dioxide we need to maintain a temperature that's good and productive for life on the planet. If with lower carbon dioxide concentrations in the Earth's atmosphere, you end up with more ice, more snow, more energy reflected back into space, and a lower global temperature. So again, some carbon dioxide good, too much bad. You get the opposite. So we pretty much know that if we pass the threshold of 1,000 parts per million of carbon dioxide in the atmosphere, that large ice sheets will not be able to exist anywhere on the planet. The global temperature will simply be too warm to support any ice on the Earth. That's not going to end life on Earth, but it will greatly increase sea levels. I don't know. It might make Antarctica a hot beach spot. I don't know, but it's certainly going to change the nature of life on this planet, especially in the United States, where we have millions and millions, if not billions of dollars of infrastructure and living right on our coastal areas, where if the sea level rises 10 feet, a lot of those coastal areas, they're going to be inundated with seawater. We may not be able to protect all that property and all those assets to where we enjoy, living in those coastal areas. And some large cities could be underwater, like Miami and New Orleans, things like that. Again, this isn't happening super fast, so we might be able to move people in those cities, but that comes at a big cost, obviously. Less ice, higher sea levels, of course. Less ice also means less energy being reflected back out of the atmosphere. So that also accelerates the warming of the Earth. So all in all, you get these positive feedback loops that increase the Earth's temperature, basically lead to difficulties for life on Earth. Again, doesn't make it impossible, just makes it more difficult. Where we get some of our historical records from, we've only been keeping paper or digital records, basically temperature records. Benjamin Franklin basically started that in the United States in the late 1700s. So compared to, the climate changing, we're talking about climate changing over thousands of years. We only have human records of temperature changes for about the last 200 years or so that are widespread and accurate enough to track temperature changes. So some of the data sources we have to turn to are things you've probably heard of. Some of those are ice core records, analyzing the layers, the changes in the layers of ice as we, basically drill into glaciers on the planet. We can see some of those changes in the, and the layers of ice can tell us something about what happened in the Earth's history, because the ice has been there so long. The ice has been most consistent, of course, in Antarctica. So Antarctica is a very important resource for us to understand the climate and the climate changes of Earth. We have about 800,000 years worth of climate record in the ice cores from Antarctica, which is why we have a research station there, at the South Pole. The Amundsen Scott Research Station, I think. And it's kind of interesting. They give their temperature about every 6 hours. So it's interesting to see when it's minus 80 degrees there. It's hard to imagine those types of temperatures on Earth, but they do still happen there in Antarctica. In some of the data in those ice cores, we can get the actual composition of the air from air bubbles that are trapped in the ice. So we can see how much carbon dioxide, methane, sulfates, nitrates, were in basically in those ice cores. We can see deposits of dust and ash that happened during periods, of more volcanic activity. In Greenland, we've got about 100,000 years worth of ice record. And we know since, from some of those ice core records, Since our last ice age, we've had 20 degrees Celsius of warming since the last glacial maximum. So, a lot of those glaciers during the ice age created what we call the Great Lakes now, and left, large deposits of rock and salt along the, edges of the Great Lakes, northern Ohio, upstate New York, places like that. When we're comparing timescales, during the tectonic timescale, global mean temperature cooled 5 to 10 degrees Celsius over the past 50 to 100 million years. Almost no impact at all on modern temperature trends. The orbital timescale can basically explain 1 degree Celsius of cooling over the past 6,000 years. It has a more pronounced variation when there's more ice present. That's, again, the reflective effect of ice, reflecting some of the sun's energy back into space. On the decadal timescale, our more active sunspot cycles can explain up to 0.2 of a degree Celsius of warming. It's in the 20th century. And then again, warming since 1900, largely we can explain that by looking at increases in the atmospheric concentration of greenhouse gases. And so the two big ones are going to be carbon dioxide and methane. Water vapor, of course, is also a greenhouse gas, but that hasn't changed a whole lot in concentration. Nitrous dioxide and ozone near the ground, that makes for more miserable living conditions than actually acting as a greenhouse gas. But ozone near the ground is what we call smog. So that's what happens in those urban areas when all that carbon dioxide gets trapped under an area of high pressure, and the sun's energy breaks down some of the oxygen into ozone. And of course, chlorofluorocarbons, we have cut down on those a lot. A lot of those were real big. You heard about those a lot in the 80s, in the 90s, as things like hairspray, right? Just were releasing, and old refrigeration techniques were releasing lots of chlorofluorocarbons into the atmosphere. And it was partially responsible for destroying the ozone layer. On this graph here, you can see over the last 100 years, on average, we started off cooler than normal for the global temperature. We had some, variations in the El Nino, Southern Oscillation, explaining some of the variability in the mid 20th century. And then despite some volcanic eruptions that typically result in large scale global cooling, we've had an upward temperature trend over the just the last 30 years of the 20th century. Oops. Okay, so climate and the greenhouse gases. Again, we've talked about this, but the greenhouse gases, what they're doing is they're absorbing heat and then radiating that back down to the surface. So just like the glass in a greenhouse, it's trapping heat, but it's absorbing heat and then re-radiating that back down to the surface. So it's actually serving as a source of radiation in addition to solar radiation. And so that's why the temperature increases. Again, the biggest forcer is carbon dioxide and water vapor. Water vapor hasn't changed that much, but in general, the hotter the Earth gets, the more water vapor we'll have in the atmosphere. So that will have some positive feedback as well. And as I explained earlier, some natural greenhouse effect is necessary for life on Earth. We don't want snowball Earth. That's not good for anybody, but we've got to maintain a healthy balance. The biggest concern is that human activities are enhancing the greenhouse effect. Here's the atmospheric CO2 concentration at the Mauna Loa Observatory. And again, we can see parts per million. We've gone from 1960 with 320 parts per million to currently 412 parts per million. And that's just over the past 50 to 60 years. So we are seeing a big increase in the atmospheric concentration of carbon dioxide. And these are direct measurements now. This isn't digging into ice cores. This is a consistent record of measuring the chemical composition of carbon dioxide in the air at a laboratory, at a United States laboratory. If we look at CO2 during ice ages and warm periods for the past 800,000 years, this is primarily going to come from those Antarctic ice cores. We can see that we had a huge dip in carbon dioxide during the ice age, where carbon dioxide was down to about less than 200 parts per million. And then, we had a mini ice age going back a few hundred years, where, again, we dipped down to about 200 parts per million of carbon dioxide. Since then, we had the Industrial Revolution, and we can see that we have just demolished the previous record for the highest concentration of carbon dioxide in the last 800,000 years, primarily due to what we think is just human causes, industrialization. On natural causes, you can see the ups and downs of natural causes in the carbon cycle, and there are some pretty big swings of about 100 parts per million. But what we've done just in the past 30 years has just launched the amount of carbon dioxide beyond anything that we can measure, directly measure in the past 800,000 years of the Earth's carbon cycle, which is what we reliably have records for from ice core samples. And again, I think I mentioned during the very first part here, as that, going back millions and millions of years through fossilized records. And again, since they're not ice core records and we can't directly measure the composition of the air, we can only make scientific guesses for what was happening. But when we had some simpler life forms on Earth, the Earth was much warmer. We did have significantly higher concentrations of carbon dioxide, but the Earth existed in a very different way. Life on Earth was in a very different form than it is now. As we get closer to more recent history, again, our direct record of carbon dioxide concentration of atmosphere comes from ice cores. So that's about 800,000 years ago. And then, you see pretty steady for human life on Earth until the last really, 50 years or so, to where we've started to see a huge increase in carbon dioxide concentration within the atmosphere. And then the forecasts for what carbon dioxide emissions are going to look like in the future are based on what actions we decide to take as a global community to reduce carbon dioxide emissions. Worst case scenario, we do nothing. That's sort of that top red line there. We get up close again to 2,000 parts per million when we didn't have life that was as complex as it is now on Earth. So we don't really know what the impacts would be. Probably not good, but we just don't know for sure. And again, this gives you an idea of when industrialization started, when Homo sapiens were first fossils were found on the Earth. So just to give you an idea of how far back the climate record goes. And carbon dioxide has increased a lot since the industrial era. So have other greenhouse gases, methane, nitrous oxide. Some of that is just because we have more life on Earth producing some of these things. Some of them are industrial, being produced by industrial means. But some of them are from having more cattle on Earth, for instance, to supply meat to the entire planet. Things like that you wouldn't think of produce a little bit extra methane than what we would normally have, which is a big greenhouse forcer. Changes in the radiative forcing in the atmosphere. Again, we can see that carbon dioxide accounts for a lot of it. Ozone isn't changing things a whole lot. The surface reflectivity is changing based on the land use characteristics. Basically, the more blacktop we put down, things like that, the more energy that the Earth's surface stores. But even that is not a huge forcer for the explanation and the increase in temperatures, of course, especially over the last 50 years or so. The biggest thing is the greenhouse gases. It's, the largely carbon dioxide, but also methane and nitrous oxide as well are the biggest things that we can see that are actually explaining the increase in temperature. And again, this is global temperatures increasing from records that we have since the late 1800s. We can see from a base of global temperature average over that time span. We can see that just even over the last decade, we've seen temperature averages increase on the order of 2 degrees Celsius over the entire planet. So we've seen, more extreme hot days, more extreme hot nights than we have seen extreme cold and extreme cold nights. And this is basically the same graph all over again. So this is basically breaking down observations and factoring in breaking down natural and human factors. And you can see based on the temperature observations, they very closely follow the combination of natural and human factors. Whereas if you follow sort of that green swath there, natural factors only would basically keep the global temperature pretty close to zero if it were not for what humans are basically doing to the planet through industrialization largely. Symptoms of climate change. So 10 indicators of a warming world. Of course, we have increases in air temperature near the surface, what we call the troposphere. We have melting glaciers, decrease in snow cover. The temperature over land is increasing just based on, thermometers. We see sea level increases. The ocean heat content increases. We can measure that through sea surface temperatures and the decrease in sea ice. In general, the hotter the Earth is, the higher the humidity, the more water vapor that exists over the Earth, which of course leads to the possibility of heavier rainfall events, bigger tropical cyclones, more extreme weather events in general, just due to the fact that we have more water vapor in the atmosphere. And the stratosphere itself is cooling, which is not great. That might indicate some degradation of the ozone layer, which wouldn't benefit anybody. That would negatively impact all life on Earth. All life is pretty much carbon based. Shortwave radiation will destroy carbon bonds, so that's bad for everything if the ozone layer gets depleted too much. So how the averages affect the extremes. So if we take a look at statistics here, this is your standard bell curve. So if we were to take a bell curve and look at temperature, if we were just considering, the Earth was experiencing normal conditions, on your average, you'd spend most of your time within the average range here, which is going to be more than 90% of the time. You would, of course, natural cycles, you'll still have extreme hot periods, but you'll have just about a balance of extreme cold temperatures as well. So, we know from stories and stuff that back in the late 1800s, we had some really extreme cold events that affected the United States. And this particular, climate scientist, Dr. Bousted, she's also done a lot of research on Laura Ingalls Wilder and her books, and her talking about some of the great winters and the long winters of the late 1800s that had a huge impact on society. So we had extreme hot periods throughout the history of the United States here, which again, only going back a couple hundred years, but they were also balanced by extreme cold periods. What we're doing, the increase in probability of extremes with global warming is we get more hot weather, more record hot weather, and less extreme cold weather. It doesn't completely go away, but it happens much less frequently. So we get much more frequent occurrences of prolonged times of hot weather and more record hot weather than we do prolonged periods of cold weather and record cold weather. The same thing if we're looking at the probability of occurrence of extreme precipitation events. Again, on the left-hand side here, this is what it looks like on a normal Earth. We still get heavy precipitation events and flooding. We still get extreme floods and things like that, but they happen a very small percentage of the time. And more importantly, we have about an average occurrence of light precipitation events or a very dry period. So we have periods of drought and less frequent periods of heavy rainfall events and flooding. With climate change, it changes the probability of occurrence of heavy precipitation events. It makes flooding more the average, and extreme precipitation events, extreme flooding events happen even more frequently. And, we've seen that, we've seen evidence of that just in the past few years here. Harvey put a record amount of water over South Texas. Really just an unbelievable amount of water fell over the Houston metropolitan area, anywhere northeast of Corpus Christi there. Of course, who could forget the Arkansas River flooding of last year? And that didn't even happen in Arkansas. That was from heavy rain falling across Kansas and Oklahoma. And then we had record Mississippi River flooding, years before that. And of course, we don't hear about it as much because it doesn't affect us here in Arkansas as much. But in the upper Mississippi River, basically in the Midwest, they've had extreme flooding impacts that eventually made it down to the Mississippi, but that only affects a very small portion of Arkansas. We've also had record flooding across the Black and White River basins, which again may not affect us here directly in central Arkansas, but it has an indirect effect in that it has a huge interruption of our agricultural land, which is largely concentrated in eastern Arkansas. Those flooding events make it difficult to plant, make it difficult to sustain crops, and make it difficult to harvest crops when needed during the fall. So, when we have those prolonged flooding events along the Black and White River basins, even if it's not directly the Mississippi, it affects our ability to make food and sustain farmers and agriculture in general across the state. And along with the heavy precipitation in some areas comes a much higher frequency of less precipitation in other areas. So not only do we have more extreme areas of flooding and heavy precipitation in some parts of the country, but we also have more extreme cases of drought in other parts of the country. So, and again, we saw this several years ago where California was in danger of running out of drinkable water. Well, they've had heavy rainfall events since then, which sort of saved them, but they had a severe period of drought, which led to California only having a couple of years left of drinkable water, which luckily changed for them. But that's hundreds of millions of people that almost ran out of water in this country. Again, looking at global temperature analysis. It's not just measuring temperature across the United States. There are a lot of climate skepticists say that in the United States, temperature sensors are placed in bad locations, and that's why we have global warming. But it's not just us measuring temperature. NOAA global temperature analysis is right in line with what they're measuring in Europe, what they're measuring from space, from satellite observations. So, what we're measuring here in the United States, it's not just the placement of thermometers. The increase in temperature has been measured across all meteorological agencies, at least that share information with us, really across the Northern Hemisphere. And again, across the Northern Hemisphere, we can see that, I'm not going to read through all those sources of data, but you can see in general what's happening for the past 50 years. We've had a pretty steady climate record, a period of below normal temperatures with that mini ice age, in the 15 to 1700s. But then we just see this dramatic increase in, in global temperature associated with the last 50 years. It's very impossible really to explain by any natural cycle. We can't find anything natural that's changed besides, humans releasing, large amounts of carbon dioxide into the atmosphere.
Can I ask a question?
Yeah.
I'm sorry. It's actually a question from somebody in the audience.
Oh, sure.
Yeah. So David wants to know if the O2 levels stay at 412, how much warming can be expected, and what's forcing the delay for CO2?
Okay. So the 412 is that would be 0.0412% of carbon dioxide in the atmosphere.
Mm-hmm.
So that, if that were to stay the same, we probably wouldn't warm any more than what we have right now. But that 412, it keeps increasing every single year. And it even outpaces some of the models we have for how much carbon dioxide we're supposed to have in the atmosphere.
Oh.
So that's, the more carbon dioxide we have, the faster, or, we're going to accelerate the warming of the Earth. I guess eventually that could lead to a lesser amount of oxygen available to breathe, but that's not really a major consideration. Just even if we got up to 1,000 parts per million of carbon dioxide, we would still have plenty of oxygen to breathe, and for plants, for life on this planet. And of course, plants use carbon dioxide to create oxygen. So I think our oxygen levels would be okay. It's just the buildup in carbon dioxide would accelerate the warming on the planet, which is going to have major impacts for sea levels and just extreme weather events and periods of hot weather in general.
Thanks, Dennis.
Yeah, no problem. And so El Nino is something that we know has an impact on global temperatures, but even factoring in variations of El Nino, we can see from 1980 through the early or through the mid 2010s here, that the average temperature has just been steadily increasing. Of course, there's just like that walking the dog analogy, there's increases and dips, as we factor in the El Nino Southern Oscillation, but in general, that trend is an upwards one. So El Nino does have a big impact on what we experience in terms of weather in the United States on the order of months, but over the course of decades, we just see an ever increasing trend in temperatures across the United States. Here's recent temperature trends. Again, just looking at the past, 20 to 30 years compared to 1900 to 1960, we've seen the temperatures across the United States increase, especially across the western and northern United States, increase by about 1.5 degrees Celsius. If you're looking for temperatures in Arkansas that have changed, you can see that Arkansas itself hasn't had much of a major change in temperature over the past 100 years. And that's the thing about global warming, is it doesn't necessarily mean every place on Earth is going to have warmer temperatures all the time. In Arkansas, we may not experience global warming as a steady increase in temperature, but we may experience some of the other impacts of global warming, which is heavy precipitation events or more extreme weather events, like higher frequency of severe thunderstorms, large flooding events, things like that. That might be more noticeable across the southeastern United States in general than across the northern and western United States. The problem with the northern and western United States is that that's the source of our cold air. So you would expect to see less severe winter weather events, less cold outbreaks, which from my experience of, living in Kansas, Dallas, and Arkansas over the past 15 years, we have had cold periods and some snowfall events, but only a couple, maybe one or two really major winter weather events. I know 2012 here was real bad, and then we had some ice storms in 2009, but talking about over the last 20 years or so, those extreme events have been pretty limited compared to the amount of high-end severe weather events and flooding events that we've had. If we look at recent trends, this is just in Nebraska, but one of the biggest things that we see across the United States, this was part of Barb's research, which is why she went to the University of Nebraska to get her doctorate, which is why this is showing Nebraska here. But more so than seeing a big increase in max temperatures, we do see an increase in basically warmer low temperatures. So we're not getting as cool overnight as we have been, especially during the winter, spring, and summer months. For whatever reason, the fall, and I don't know if this is different in Nebraska compared to Arkansas, but at least in Nebraska in the fall, they were still getting some pretty cool overnight temperatures. But in general, those overnight temperatures were really warm. And this, I know in the Dallas-Fort Worth area, having done some research there, the land use changes had a huge impact on overnight temperatures. Their overnight lows there are 5 to 10 degrees warmer than what they had been historically. And a lot of that is not necessarily due to global warming as it is to local land use changes. There's hardly any green spaces in the Dallas-Fort Worth area anymore. So it's almost all concrete and brick, and that stuff just holds on to heat. And at night, it radiates all that warm air out into the Dallas-Fort Worth metroplex, and it just stays warmer overnight than it would, again, without all the concrete and brick in the area. And again, it's more than temperatures. As we're looking, across the world, across the Northern Hemisphere, where we have most of our data, and even across the United States, we can see sea level rises and coastal flooding impacts increase in frequency. We see the Arctic sea ice extent has been decreasing steadily throughout the years. And, if I don't know if you've ever watched the show, what's it called? Where they go out and collect crabs in the Alaskan waters there. The sea ice encroaching, on the boats there around Alaska, even that was becoming less frequent as that show progressed over the past 10 years. So the Arctic sea ice extent has been steadily falling, which, I guess it may help some of those fishermen collect more crabs more frequently, but it does have negative impacts on natural life there. Polar bears especially have less area, places to hunt, to get seals, things like that. So you do see a negative impact on some of the natural wildlife in the area, and of course possibly to some of the humans as well, as you see. Sea level rises along coastal areas, which are typically very high value property. One of the big things that we've seen, especially in the United States, is a pretty steady increase in billion-dollar disasters. That's adjusted for inflation. So, and a lot of that you can see is from severe thunderstorms and flooding have accounted for a much higher impact on billion-dollar disasters across the United States just in the past decade than they have, throughout the history of measuring such things, which has really increased, in the past 30 years or so. So our amount of billion-dollar disasters has a big impact on our economy. And, when we have a big hurricane season, like we did with Harvey and Maria, that has a big impact on our economic climate and how much money we have to put into support for recovery for these areas that experience extreme weather events. And of course, severe thunderstorms, hailstorms, windstorms, tornadoes, they become more frequent as well, again, across the Northern Hemisphere in general, which leads to more disasters, more recovery, higher insurance rates, and things like that. And, the tropical cyclones, we do see an increase in that, but also wildfires is a big one, especially out west. It doesn't affect us here in Arkansas really, but out west, they've had some huge wildfires. And we even saw the community of Paradise in California got completely wiped out by a wildfire in the past year or two. So wildfires are becoming a lot more frequent as well. And while wildfires are normal, that's a part of the normal cycle of things that happen on Earth. The extreme wildfire behavior is something that's increasing more, encroaching more in society than it ever has in the past. Precipitation trends, basically, again, the last 30 years compared to the previous 60, we've seen much higher precipitation totals in the upper Mississippi River Basin across northern, north central Oklahoma, south central Kansas, which feeds into the Arkansas River. And again, in Arkansas, we're half and half. Precipitation across the state itself hasn't changed all that much. But upstream, upriver, we've had more extreme precipitation events, which ends up affecting us here in Arkansas, even if we don't get the direct heavy rainfall events. And of course, out west, where you get some of the more extreme wildfire behavior, you've had more extreme droughts as well. When we're looking at snowmelt is occurring earlier than normal, which has a big impact on how much and how frequently fresh water is available downstream. A lot of areas rely on snowmelt to keep replenishing local rivers and lakes with a fresh water source in order to support the local population. So an earlier snowmelt might mean less available fresh water for usage, later into the summer and into the fall. Snowpack in general is declining across the United States. So you can see all the red dots is basically a percent change in the amount of snowpack, and the blue dots are an increase in snowpack. So there are some areas with an increase, but outside of having less available fresh water, it affects the ski industry. You don't have as much snowpack, so you don't get the same amount of tourism and I guess good ski conditions as you do in some of those high-priced areas in Colorado and in some of the more mountainous areas of California and Oregon. So that has an impact on economy and available fresh water. Again, looking at Arctic sea ice extent, we've seen a big decrease in that in the past 30 years. And again, multi-year ice is just decreasing in general. Basically, the ice is thinning. And in general, the September Arctic sea ice extent is declining at a rate of 13% per decade. So that's pretty huge. If it continues at that rate, again, you wouldn't have any sea ice if that continues for, another few decades, really. There just would be no early sea ice at all. We're looking at just the United States. This is having a big impact on low temperatures. The minimum temperature throughout the summer has been steadily increasing, which across the whole United States, we usually rely on cool nights to offset the hot days. And without the cool nights, it just makes things more miserable, especially for if we have an increasing homeless population or any vulnerable population that can't afford central air conditioning. It increases the likelihood of fatalities to homeless and the elderly. If they're living on a fixed budget and they can't afford central air, or if they generally open the windows and turn off the air conditioner at night, you don't get as much relief, and you end up with a higher fatality rate for the homeless and again, more vulnerable populations to warmer overnight temperatures. As I mentioned, big rain, heavy rainfall events are increasing. In general, you look at, again, the last 50 years compared to the long-term average, we've had more real heavy, high-impact rainfall events, than we've had, just in the recorded history of our country. We didn't have a long historical record in Alaska to compare things to, but Alaska doesn't, our climate network or observation network isn't great there anyways. But, we look at some of the modeled changes in high impact precipitation events, and, you can see that, again, our do nothing, basically current order of business, that RCP 8.5, the percent change in flooding or high impact rainfall events would increase by almost 40% in areas upstream, upriver of Arkansas, and, in some parts of the Northwest and Northeast United States as well. There's heavy rainfall events is one aspect, but there are other aspects of climate change as well. It does also impact the number of frost-free days that we have, which some people might consider good. It all depends on your perspective, but again, that has a higher impact when you go further west and further north, where we just have less days without frost, before we see our first frost, and when we have the last frost during the warm months. Here's some of the projected temperature changes. This is what we've currently observed right here in the middle. And again, in Arkansas, you can see that's pretty neutral. If we start to do something about it by the late 21st century here, so by the end of the 21st century, we can, if we start to control things, the change in temperature is still going to be positive, but it might only be on the order of a couple of degrees Fahrenheit, where this, again, RCP 8.5 is where we do nothing. And you can see that has a really extreme change in temperature by the end of this century here, where we could see temperature increases on the order of 7 or 8 degrees Fahrenheit or more across the United States. And again, I hope we end up agreeing to doing something better than do nothing, but it's until we start doing something, that do nothing projection is, might be the best that we have. Precipitation changes. Again, this is what we've observed, and this is some of the projections. You can see across the summer, we might be more, have a higher likelihood of experiencing drought, especially in the northwestern United States, where we could get wildfires that time of year. During the spring, a higher incidence of precipitation. And in the winter, which might make you think you're going to get more winter weather, but if it's warmer, again, it could just be rain. So during the spring, we get more precipitation. In Arkansas, especially, we might get more severe weather as well. But I think the big thing is overall, we might still get rain in the west and northwest, but it just depends on the time of year. If you get more rain in the winter and spring, that leads to bigger vegetation growth. You get a drought in the summer, that leads to drying out of the vegetation, and then more wildfires. So it's, not a great cycle to be stuck in. Here's the trend in tornadoes, some of the researchers have put together. This is basically where it's projected that we'll see a higher incidence of tornadoes given recent trends in climate change. And unfortunately, this is where Arkansas comes into play. We're not necessarily the epicenter of where we expect to see more or the most tornadoes, but you can see that maybe a lesser incidence of tornadoes in the high plains, basically, just east of the Rockies there, and eastern Colorado, the Texas Panhandle, and things like that. But a much bigger increase in tornadoes across northern Arkansas, and then as we get into the Tennessee Valley and into the south central United States, Mississippi and Alabama, you can expect to see a higher degree of higher end tornadoes, as the earth continues to warm here. Basically, the warmer the Earth is, the more water vapor the atmosphere can store. Water vapor is basically energy for thunderstorms. The more energy you have for thunderstorms, the higher your possibility of bad thunderstorms. And, one of the scary things here is the probability of increase of violent tornadoes. It sort of centers itself over, far eastern Oklahoma, maybe far western Arkansas. So that's a trend we wouldn't really like to see, continue here for the next, few decades. But that's about all I've got for climate change. Do y'all have any questions after all of that?
Yeah, I did. One question did come in. Just a question about the global effects of permafrost and tundra.
Oh yeah,
in the northern areas.
Yeah. So let me go back here a little bit. So, if we look at those areas, again, if we look at that, if we do nothing, that RCP 8.5 range there, we see that the northern United States, you can imply that goes into Canada, and across all of Alaska, we would expect temperature increases on the range of 7, 8, or higher degrees Fahrenheit by the end of the 21st century here. So the changes in your permafrost, certainly you would have areas that simply wouldn't have permafrost anymore. So that could lead to a big change in soil conditions in those areas. It could lead to some agricultural opportunities further north, but some of that permafrost to some of the wildlife depends on that to exist. So you'd have, again, the problem is you have the earth changing faster than nature can keep up with it. So you would probably on average end up with, a bigger impact to wildlife and a negative impact on life than what the earth can adapt to in general. But you would expect in general to see less permafrost and less tundra. We don't really have tundra in the northern United States, but in Alaska, we certainly do. And then in Canada, the implication is that would be greatly impacted as well.
And isn't there a lot of carbon dioxide and those kind of gases trapped in that permafrost? Wouldn't that be released as well?
Yes. Yeah, that's
the problem true. Even worse.
Yeah, so we do have carbon dioxide stored in the oceans and in the ice caps. And so permafrost counts as well. So yes, that would be another source of carbon emissions, which would help partially explain why you expect so much of a higher increase in temperature change in areas up north than compared to areas down south. Part of that is just because they're colder, and so you get the more extreme temperature changes there. But yes, you would accelerate the emissions of carbon into the atmosphere as well.
Okay, thanks. Here's another question from Sarah Ray. She said, I heard that due to social distancing, CO2 and greenhouse gas emissions have significantly decreased. Could that have a positive impact on global warming, or is it an insignificant amount, or too little too late?
Well, we have seen a decrease in CO2 emissions here in the short term, and we saw that especially over China, but that was in the Wuhan area. We saw an incredible decrease in carbon emissions and in smog, a huge increase in air quality, but that's because China essentially completely shut down their society there, where you had less carbon emissions because they also shut down all industry. It wasn't just people not driving around as much, but they didn't have any industry output as well. China has since relaxed some of those restrictions, and the air quality has decreased pretty quickly again. So, it is true that due to the social distancing and people having to stay at home, it is having a short-term increase in air quality and decrease in carbon emissions, but it's not sustainable because our economy can't really account for people staying at home. There's only so much work you can do from home, and manufacturing is one of those things that you can't really do from home remotely. So at some point, society will have to return to normal for our economy to return to normal. And that will, again, unless we've made some substantial change to go to clean energy sources, we'll see those carbon emissions increase right back to where they were. In the short term, it is helpful, but again, it's not sustainable. It's not something we can do on the order of years, which would be necessary to have that large impact, to see some of that, like that lower scenario, RCP 4.5, that relies on us sustaining lower carbon emissions on the order of decades, not just in order of months, what we're likely to see with this pandemic here.
I like to think of it as an example, though, for people who don't believe that we're impacting the environment.
Oh, yeah.
It so clearly, changes quickly when we stop impacting. But anyway, that's my editorial.
Yes.
I have a question from Cindy. And she says, this is totally random, but how significantly does the increased rate of cremations affect global warming?
In general, I don't think that's very significant. The increase in the number of cremations, it's and I just don't see it being sustainable enough to have a big impact on. I mean, that's a one-time event, right? You cremate somebody and then that's pretty much done. Obviously, people we've got more population, people are dying more frequently, and so you have more cremations, but overall, the people that are alive and driving to and from work and participating in industry and fracking, drawing oil from below ground, living people are having a much, much, much greater impact on the earth than people that have deceased. So I don't think the increase in cremations has really any impact at all on carbon emissions. It would be very minuscule compared to what everybody is doing collectively that's alive here on Earth.
Great. Thanks, Dennis. Another question. This one says, what are some sustainable measures individuals can do here in Arkansas to try and decrease CO2?
So yeah, that's a great question. And that's a great question everywhere. And, some of the minor changes that we're aware of is, you can try to lower your electricity usage. And that can be anything from, trying to, during the summer, trying to deal with a slightly warmer house instead of setting your thermometer down to 71, maybe keep it at 74, 75, something like that. Anything that uses less electricity can help decrease carbon emissions, not because your house isn't producing carbon emissions, but those power plants are. So if you use less electricity, there's less carbon emissions by the power plants, which indirectly reduces carbon emissions. Other things you can do is, if you can get somewhere without driving your car, that helps. If everybody were to do it, it's small for any one person, but if everybody were to do it, it would add up. What would really be great is if everybody was able to switch to a clean energy source. Like if we had a much greater, incidence of solar panels on roofs or wind energy, then using things like electric cars would have a much greater impact on society. But that requires a huge change in our infrastructure. We'd have to replace gas stations with electrical charging stations, and you might have to have electrical charging stations in each home and at every business just to make sure that you didn't get stuck, right? So that would require a very large change in society, which you may not have direct control over, but solar panels on your roofs, maybe changing your light bulbs from normal light bulbs to the LED light bulbs that uses less energy. They last longer. Some of it is managing trash. If you don't create as much trash, there's less landfill usage, less carbon buildup in some of the areas that burn trash to get rid of it. So there's little things that we can all do that can have a small impact, but then, when we combined all those impacts, it makes a larger difference. And that's sort of where the theory behind that lower scenario, the RCP 4.5, comes from. Our society holistically making changes to reduce our carbon footprint. And there's using less energy. That, I mean, you can be more efficient, make sure you have good insulation in your home. Try to get a more efficient air conditioning system, heating system. And again, if you can make short trips on bike or walking, or not drive your vehicle, that every time you can do that, that has a greater impact. So if you have a neighborhood pool, if it's a half mile down the road, if you can walk there instead of drive there, that's a little bit that helps. So every little thing that we can all do helps. It's just convincing everybody to try to do a little something that's going to make an impact. And that's where we find our biggest challenges, I think.
Thank you, Dennis. Those are all great ideas. There are no more questions at this time. So if we want to take a little break.
Yeah.
Okay. Thanks.
Sounds good.
know, when you wore gloves shopping. Hey y'all, this is Ann. Lynn, if you are there, if you are logged on as Lynn's iPad, would you please let us know who you are so we'll know where to send an email for the evaluation. You can either do that in chat or just unmute yourself and say, oh, it's me, I'm Lynn's iPad. Thanks.
Okay, sorry. Couldn't figure out my unmute button.
It happens.
Okay, did you want me to continue on?
Please.
Okay. Okay, so part 3 here is going to be more focused on climate communication. There's certainly a scientific consensus, and we'll talk about that versus public understanding, and then talk about maybe ways to communicate climate change to people that you know, may not be receptive, or you know, may not trust the science of you know, of climatology and climate change in general. Oops. So the language of climate change, you know, some of the terminology that we use is, you know, basically the researchers in the field, they prefer the term climate change as opposed to global warming. They're often used interchangeably because that's what's happening, is the globe is warming. But global warming is, you know, more politically charged than climate change is. And climate change does more accurately describe the changes to the entire system and doesn't just focus on the temperatures itself. Many people will still say global warming anyways, because again, that is what's happening at its core. But you know, again, it's some of the solutions are difficult, which you know, makes some people not want to accept that climate change is happening. So, you know, as the cartoon indicates here, utopia theory, yeah, the big elephant in the room, right? We see them, but nobody wants to talk about it. We're very hesitant to make big changes to society for something that we don't see changing in the short term. So, you know, something like a pandemic, we see that changing on short-term periods, and you can see as things get worse, people make very quick changes. But if you don't see it getting bad very quickly, you're slower to make changes. And you can even see that with some states. There are several states that haven't implemented, you know, big restrictions on, you know, on sheltering in place and things like that, maybe even avoiding churches. Because they haven't seen their numbers increase that much. And that changes when you see bad things happen. So as things get worse, people react to it more strongly. But one of the challenges with climate change is that it's happening over such a long time period that people are reluctant to react to it, to make major changes to their life to deal with it. One of the things you want to be careful about, of course, is being very careful about your information sources. Of scientists that study climatology, 97% agree that the climate is changing, and that climate change involves a warming Earth. And as with anything, with scientists, you're always going to have people that research and study and try to provide evidence for the opposite, or the the opposite to consensus, but a 97% consensus is almost unheard of for any topic of science. Science is all about, using evidence to prove and disprove things. And, what I can tell you is if somebody could disprove climate change and prove that the earth is not warming and that humans were not the cause of it, that person would be very, very rich. So there is a huge, a very big reward system in place for somebody that could prove scientifically that climate change is not happening, but that doesn't exist. So it's, besides the 97% of people that agree, the reward system there, people still haven't been able to prove that the earth isn't warming and that people don't have something to do with it. So again, be careful about your information sources. Blogs, news commentators, politicians are hardly ever trained in climate science, and they have their own reason for agreeing with or denying the actual research that goes into climate science. And one of the analogies here is, where would you go to get information or to get a procedure done if you needed heart surgery? Would you go to your dentist, a local politician, or would you go see a heart surgeon? Right? Obviously, you go to an expert when your life is on the line. So why wouldn't you do it for anything else? And climate scientists are the experts. I am not one of them. This is Dr. Bousted's presentation here. I have a good understanding of what's happening, but she is the expert, and a lot of this information comes directly from her and her colleagues. So some of the challenges to understanding our climate is that climate and science in general, the literacy is quite low. The climate, it's not something we can feel every single day. It's not necessarily intuitive. Like in Arkansas here, we're not getting warmer every single year. It's very complex. It doesn't just increase based on a line, which is a very easy pattern for people to understand. And it's often confused with weather. For instance, if we have a week of below normal temperatures, you'll get people on social media saying, oh, gee, where's global warming now? Well, a week of cold weather has nothing to do with global warming. A week of cold weather doesn't have anything to do with the 40 weeks of above normal high temperatures. And those people all of a sudden go away when the temperatures are warmer than normal. They like to pick out those times when it's colder than normal and try to use that as a basis for denying climate change. The media has had a big role in portraying this sort of protagonist-antagonist view, this two-sided debate about climate change. Within the scientific community, there is no actual debate. Climate change is accepted, and there's not that much science that goes into reproving climate change over and over again, because that's not how science works. Once somebody has proven something, you provide evidence on a different aspect of climate change, or you try to provide evidence that goes against it. And there is really no evidence that goes against what's currently the accepted theory of climate change. Unfortunately, climate change has been intertwined with politics, and that greatly complicates the response to combating climate change, especially in the United States, where the fossil fuel industry has billions and billions of dollars. And, in our political system, those companies are allowed to donate millions of dollars of money to politicians to lobby them to make decisions. So you don't have, and those politicians aren't trained in climate science. So they're much more responsive to lobbyists and where their sources of money are coming from, rather than climate science in general. It's not necessarily that politicians are evil. That's just the political system we work in. They're getting their money and their information from people that don't want to do anything about climate, that are actually motivated based on their economic model to try to deny climate change, to keep fracking, to keep pumping fossil fuels, and to keep our economy and our life running on fossil fuels. That they may understand what's happening, but they don't want their business to collapse. So they lobby politicians, which turns it into a political debate when it doesn't really need to be one. Of course, confirmation bias is something all humans are susceptible to. If you look for and find evidence for what you already believe. So if you think the climate is not changing, you'll only seek sources of information that support that belief. If you believe the climate is changing, you'll only support sources of information that support, that belief as well. And that goes for almost anything. We can all be very susceptible to that. It's hard to be objective with everything in life. And so in general, you're going to support information and find people with common beliefs towards you or towards what you believe in, rather than try to look at something objectively. Now, here's a real interesting survey. It's an older one, but these are just questions that were asked of the general American public. And this is, again, a 2001 survey, so it is a little dated, but some of the questions that were asked that, some of them, you would think would be everybody should understand, but the center of the earth is very hot. 80% of people agreed with that. I mean, I guess that's good, but why not 100% of people? I mean, that's a pretty well understood fact. So some of the things that people are more aware of is the oxygen we breathe comes from plants. So most people understand that. Yes, that's true. All radioactivity is man-made. That's not true. Radioactivity occurs in nature all the time. Yet you had a large number of people that believe that. That's definitely not true. People that the amount of people that understand that electrons are smaller than atoms, less than 50% of people. It's not so great. People that believe that humans and dinosaurs coexisted, 50%, not so great. One of the really troubling things is the time it takes the Earth to make one lap around the sun is equal to 1 year. Just a little over 50% answered that correctly. Wow. I don't even know what to say to some of that, but it speaks to some of the scientific literacy issues that we're dealing with. It's not just climate change. It's a general problem with scientific literacy across the United States public that complicates some of the communication of climate change. So here's what we know about climate literacy and what drives our climate system. Of course, the sun is the primary source of energy for the Earth's climate system. If we didn't have the sun, well, we wouldn't have life. We wouldn't have a climate on Earth that we need to worry about. We also know that the climate is regulated by complex interactions among the Earth's spheres, as we talked about very early on. Life on Earth depends on and is shaped by the climate. In large respects, life on Earth has evolved because of the climate. And when we make big changes to the climate that we can't keep up with, we have very negative consequences because we can't adapt to how quickly the climate is changing. Not just humans, but all life on Earth. Climate varies over space and time via natural and man-made processes. That is true. And it's hard for some people to understand that man-made processes are accelerating some of the bad things that are happening. The people that claim that, recent warming is just due to a natural cycle, I mean, there is a tiny bit of truth to that, but most of it is explained by man-made, people causing climate change, not just because of a more active sunspot cycle. Humans are impacting the climate system for sure. We know that. And our understanding of the climate system, of course, is going to improve through more and more research, observations, computing power, modeling, so on and so forth. And we know climate change will have consequences for the Earth and all living things on the Earth for hundreds and hundreds of, if not thousands of years to come. Even even if it may even extend past humans, depending on what we do to ourselves here on this planet. Based on research, we know that there are basically 6 categories of climate change, and some of this is based on the nature of the research, the categories that they allowed people to answer. But so, highest belief in global warming, basically the people that are most concerned about it. So you've got 17 to 28% that are concerned about it, collectively leading to 45% of people that are alarmed or concerned about climate change. Cautious, that's at least leaning on the right side. And then on the right-hand side, people that are disengaged, doubtful, or completely dismissive, that basically think it's a hoax. So associated with the alarmed and concerned, the basic demographic or political breakdown, basically independents, democratic, liberal leaning people, females, people of moderate income, Catholic and Hispanic people that tend to believe in climate change and global warming. The doubtful dismissive are typically authoritarian type people. They tend to be Republican, individualist, male, more high income, leaning high income, evangelical, born again whites that tend to dismiss climate change. Associated with the disengaged, cautious, sort of in the middle, they don't care, tend to be low income, high school educated, and more the African American community. They're not leaning one way or another. They're basically, they just don't want to be involved. The people that are alarmed and concerned are more likely to see, understand the consensus of scientists, understand and believe that most scientists think global warming is happening, which is the current state of the science. Once you get to the dismissive part, people that, basically think it's a hoax, of course, hardly any of them think that most scientists agree on global warming, which is a fact. Most of them think that there is a disagreement about whether global warming is happening or not. And some of them think that most scientists think that global warming is not happening, which is patently false. And the disengaged oftentimes just don't know what to say, which makes sense. They're disengaged, right? So they just don't care about the topic in general. Some of the solutions maybe to communicate with the less educated folks, this isn't going to improve everything, but sometimes it's just the way that we communicate science and how the public interprets that. I'm not going to go through every single thing here, but when we use terms like uncertainty, people think that means ignorance, like we don't know what's happening. That's definitely not true. That just means that there's a range of possible outcomes. Not that we don't understand those outcomes, but it's that we know that there's not going to be an exact outcome to our models, but there's a range of possible outcomes. When we say there's a positive trend, temperatures are exhibiting a positive trend over the course of years, some people may interpret that as a good thing. Something good is happening with temperatures, where what we really mean is an upward trend. So if we use terms like an upward trend in temperatures, people understand that as an increase in temperatures, not necessarily a good thing. When scientists use the term values, people typically relate that to ethics or monetary value, when really we're talking about numbers and quantity. So, so again, some words you can think of or use to replace some of the scientific words that can help the understanding of what we're trying to communicate scientifically. When we say anomaly, people may think that's an abnormal occurrence, so something that might go away given enough time. But what we really mean as science is that it's a big change from the long-term average, something that's probably not going to go away. But again, we can replace it with more plain language to keep messages more clean and simple and not as detailed, to get more of the people, especially that are not as educated or disengaged, to understanding the need for change and to take action to do something about climate change. Here's how scientists tend to communicate. Scientists like to talk about the background, their supporting details, and then at the very end, talk about their results and conclusions. The public really, they want to know the bottom line. The supporting details are kind of important, but they want to know the bottom line first, and then what do we do about it? And then the supporting details. So we can try to communicate more like a news reporter, and not a scientist or a conference presenter, when we're trying to communicate what's happening scientifically. We can focus on the bottom line, the results and the conclusions, and then provide the supporting details in the background instead of spending an inverse amount of time like scientists tend to do. One of the strategies to combat climate deniers or global warming deniers is, don't repeat what they're saying. So repeating, what climate deniers might be saying, that things, something's a hoax. Actually, if you hear a scientist repeat the hoax, that makes people believe that the hoax talk is true. So one of the things is you just don't repeat what climate change deniers are saying. You just repeat messages that or that the scientific community understands as being true. So, the climate is changing and humans are the main cause. This is what 97% of scientists agree is what's happening. El Nino, La Nina may be happening, but we may not be able to sense its impacts for several months. It's not an immediate occurrence. It's not a weather phenomenon. The 3-month temperature outlooks can tell us if the odds of, experiencing a warmer or cooler conditions are going to happen. It doesn't mean you won't have very hot or very cold outbreaks during that 3-month period. If you do have somebody that's in disagreement with you, try not to get mad. And this is actually a picture of Dr. Bousted on the right-hand side there, pretending to strangle one of her colleagues. So a nice cameo from Dr. Bousted there. But she obviously put that picture together to encourage people to use dialogue, ask questions, and listen to answers to try to understand where they're coming from, what their root causes are, and to try to diffuse emotions and political motivations. Be patient. Misinformation oftentimes comes from trusted sources. So if you have a news station that is politically motivated to deny climate science, people may trust that news source. It's not that they're being intentionally ignorant, but that news source is telling them something. They trust that news source. So don't get mad at them. But try to find some common ground and provide alternative, credible sources. And again, repeat what we know and don't acknowledge some of the messaging by climate change deniers. And when there are gaps in understanding, acknowledge those. Don't pretend to know more than what we do know. If there's something you don't know, admit to it. But there is a good state of the science. There are a lot of people researching it. There is a lot we know about climate and the way we're headed. One of the strategies to communicating climate change is to create a narrative, tell a story of climate change and how it's impacting a certain community, instead of just providing straight up facts. A story is most effective if it's congruent to somebody's life experiences. A story tends to transport listeners. That's why people love watching movies and reading books. Listeners tend to trust storytellers, and they tend to relate to protagonists. So, if you can sort of change the climate communication into a story that relates to people, you might be able to educate and encourage people to understand the current state of the science and avoid some of the political posturing that's involved in that. And some of the questions you guys asked, like pairing the science with solutions, like, okay, so what? So what do we do about it? That can help ward off denial and engender hope. If all we talk about is the bad stuff without presenting any alternatives, then people start to feel defeated. And so what difference does it make? Why should I even try to do my part if this is just going to happen? So, we try to encourage avoiding a single action bias. So replacing your light bulbs to all LED light bulbs, that's great. But, try to do something else also. Try to reduce your trash usage, try to encourage recycling. Maybe, support local businesses, local agriculture, outside of buying, everything that's imported from other countries, because transporting those goods from other countries to us is another big source of carbon emissions. So if you buy local, there's less of a carbon footprint than there is from buying stuff that's imported from, Asia or, any other part of the world. Small actions, tiered actions grow they snowball into a larger, amount of activity. So, small changes that you can make and encourage others to make, that will snowball to have a bigger impact on society as a whole. Finding credible sources of information. Some of this is just for resources for you, where you can, there's a State of the Climate report that's issued every year by the American Meteorological Society. It's pretty much published each summer. And a lot of times I know it's sent directly to people that subscribe to the American Meteorological Society. But it is led by the government climate group that's a part of NOAA, now called NCEI. And it includes hundreds of authors from many countries. It's not just American, but it's basically the current state of the understanding of climate science across the world. And it's a good report. You can get a monthly States of the Climate Science from NCEI. And again, that's if you go to ncdc.noaa.gov. There's a lot of resources there. And, some of these are just taking you to different branches of NCEI to give you some of that information. NCDC and NCEI are the same organization. They just changed acronyms over time. Other sources of information. There was a fourth national climate assessment. That's from the U.S. Global Change Research Program. You can find that at NCA 2018. I still think that's the most recent one, .globalchange.gov. It should give you access to that report. And then you can see some of the impacts of climate change to different regions of the United States, have been cataloged and, basically summarized in some of these maps and infographics that are easy to understand and share. Other sources of information, International Panel on Climate Change. There's a UN chartered group of leading scientists charged with assessing the state of climate change and its impacts. This involves not just the United States, but over 130 governments, 450 lead authors, and 2,500 scientific reviewers. So lots of people from lots of different cultures, countries, and governments all coming together to give one holistic report on what's happening with the climate. And, contributors must agree on every word of the document before it's published. And so there have been several reports throughout, the past 20 or 30 years or so. And, these are made somewhat infrequently, but basically as scientists come together and agree on something, they publish this large IPCC report. Also, there's regional climate centers that you can get information from. There's 6 regional climate centers. The Southern Regional Climate Center is our regional one, and that's going to be based out of New Orleans, I think. But there's also a state climatologist that you can get local climate data from. And there's also regional assessments that, have some data, but of course, somewhat limited coverage depending on where they are. Oops. some of the climate change tools. If you go to NCEI, you can actually look at data. And if you wanted, you could show data or develop your own charts and graphs from data. You don't have to use what I used here. You can take your own look at your own data, come up with your own conclusions, create time series to show people what's been happening for specific locations over time. You can break it down into city, climate division, state, over the United States or over the globe. And you can look at things like the temperature over time, the highs and the lows over time, precipitation. Degree days is basically a measure of how much energy we need to use to heat or cool our homes during various times of the year. All those things you can look at. All that data is freely available to you, and to make whatever chart you'd like to personally review the data that we have. It's all free and available for you. It's just sitting there. You can look at trend analyses at any time you want. And there are several modules and stuff that are free online that you can look at as well to look at climate change and climate analysis. There's a climate.gov global climate dashboard. Has a lot of really good charts and tools to visualize climate change and carbon dioxide concentration as it's measured across the globe. And of course, things like spring snow cover. You can see based on millions of square kilometers how that tends to be decreasing through time. But you can look at Arctic sea ice, the sun's energy. You'll see that that's not changing much. Glacial content and coverage, and heat trapping gases, other things besides just carbon dioxide. There's a climate resilience toolkit, basically giving you things that you can do, to help combat climate change locally or even at the state and federal levels. Guides to help you reduce your carbon footprint. And of course, if you want more information, there's my contact information, and Dr. Bousted, she also has her contact information on there as well. If you ever wanted to contact us, it's probably best to email me if you had any questions well after this. But Dr. Bousted, you can email her or give her a call. She's always more than happy to talk, climate change with folks. So you can probably contact her on email or via Twitter. She's not shy about having public conversations about climate change if folks want to go that route. So with that, that's really all I had to present you all. I'll be happy to have a discussion or answer any questions you have.
Okay, we do have a couple of questions that came in.
Okay.
From Janet, she says, what could we do about the global amount of plastic pollution, and does it have any relationship to climate change?
So the plastic pollution that comes from people basically throwing out plastic as opposed to recycling it, and that does have an impact on climate change, because some of the plastic pollution, it can make it into oceans. It can hinder, it can kill off some of the algae that produce a lot of oxygen for us. Plastic and plastic pollution, it doesn't break down easy. It comes from petroleum, so it's basically an extract from us getting carbon out of the earth. And so, yes, it certainly does have an impact on your carbon footprint. In general, the more we can recycle plastic, the less plastic waste we have, in the environment and in oceans. And nothing on the earth is permanent, so everything breaks down through time. But it takes about 10,000 years for plastic to, break apart into its chemical compounds to where it's not plastic anymore. So it's, it takes a long time for it to go away. So if we can recycle as much as possible, that certainly helps reduce your individual carbon footprint.
Thank you. And I was wondering if you could share the jargon slide with us. I thought I wanted to read through that more carefully.
Oh, yeah.
And then maybe some of the resource slides. I wasn't able to jot down some of those. If we could get those resources shared with us, that'd be great.
Sure. Yeah, that's not a problem at all. I can email Ann with those slides, and she can maybe pass them out to your group there.
Good.
Yeah.
Well, we're getting some comments about how much people have learned and how much they appreciated it. So
Okay, well,
I
great.
don't see any more questions. I just see people saying, thank you, thank you.
Okay,
Yeah.
sounds good.
Yeah.
Okay, very
Okay.
good.
Yeah, well, thank you very much. I appreciate it, and thanks for giving me the opportunity to talk with all of you today.
Great job.
you.
Thank you.
Well, thanks.
Yay. Hope you have a good rest of the afternoon. I'll shoot you an email in just a little bit, and we'll
Sure.
do this. Okay.
Okay,
Bye, Ann.
sounds good.
Bye.
Thanks, y'all.
Thank you.
Bye-bye, y'all.
Thanks. All right. Bye.
Bye.